It seems like if this person jumps out of an airplane, they're in free fall, but that doesn't quite meet the definition of free fall. To be in free fall, you have to be freely falling, which means the only force acting on you can be gravity. There can't be any other forces. And air resistance is a big force that we do have to deal with. But one thing about air resistance is the faster you go, the more air resistance you feel. Stick your hand out the window of a car going 5 miles per hour, not a lot of air resistance. Stick your hand out the window of a car going 80 miles an hour, a lot of air resistance. So when you're traveling slow, there's not a lot of air resistance. So we're going to pretend that free fall, that if you drop an object, it is in free fall initially, because there's not a lot of air resistance initially. So my question here is, do objects in free fall accelerate? And it may seem that it's a simple question or the answer is obvious, but yes, it does accelerate, but how would you prove it? What evidence can you cite to actually show that it did accelerate? Well, it might be good to come to the definition of acceleration. Remember, 3 little lines means it's the definition. So if I hold that ball in my hand and it has no velocity and I let go of it, and a moment later I observe that it has some velocity, well, I just observed that it changed its velocity in a period of time. So yes, it did accelerate. The question now is, do objects in free fall accelerate uniformly? So I need to talk about what I mean by uniform acceleration. In the last video I showed you of this motorcycle accelerating from 0 miles per hour to 220 miles per hour in 25 seconds, and we calculated the acceleration of that motorcycle. It was defined as a change in velocity over time. Slope is defined as rise over run, which is a change in the y-coordinate over a change in the x-coordinate. So it looks like the slope of this graph is going to give us the acceleration, because on the y-axis we have velocity, on the x-axis we have time. Well, it's a change in velocity over a change in time. And if I were to find the slope between the starting point at 0, 0 and the ending point at 25 seconds and 220 miles per hour, the average acceleration would be 8.8 miles per hour seconds, or miles per hour per second. Algebraically, it's the same thing. Now, the acceleration of the motorcycle was not uniform. We see here this blue line had a steep slope, so it had a large acceleration there, and over and through here the slope was not very steep, so it had a lot less acceleration. But the motorcycle would have been in uniform acceleration if the instantaneous acceleration was the same as its average acceleration over the whole time. If after 1 second it was going this fast, and 2 seconds it was going this fast, and 3 seconds it was going that fast, and so on, if it had changed its velocity by the same amount every second, then it would have been in uniform acceleration. So an example of uniform acceleration would be if something is accelerating at 3 meters per second squared. Just a reminder of what that means is that it would change its velocity by 3 meters per second every second. So every second the velocity changes by 3 meters per second. So every second that goes by, the velocity went from 0 to 3, it changed by 3, it went from 3 to 6, it changed by 3, and every second that goes by, it changes by the same amount, and the velocity changes by the same amount. There's a neat activity you can do fairly simply by just setting these flags and creating a course to run through. If you had a strobe light or something that would flash once every second, and you set these two flags 1 foot apart, and then 2 feet, 3 feet, 4 feet, 5 feet apart, and you went from the first flag to the second flag in 1 second, you were traveling an average of 1 foot per second. And then if you go from the second flag to the third flag, this time 2 feet in 1 second, you were traveling 2 feet per second. And then 3 feet per second, 4 feet per second, 5 feet per second. As long as you are at one of these flags every second, you would have been accelerating uniformly. Now, if you are at a stop here, and then you're stopped here, and then you're stopped here, and then you're stopped there, and stopped there, meaning you sped up and slowed down, that wouldn't be uniform acceleration. But if you smoothly and uniformly changed your velocity by 1 foot per second every second, you would have had an acceleration of 1 foot per second, 1 foot per second squared. So if you start here and you race through the course and you go faster and faster and faster and faster and faster, smoothly and uniformly, then that would be uniform acceleration. And you don't have to be at the flags every second. You could be at one of these flags every half second or every 2 seconds. It would have still been uniform acceleration, but you would have just had a different value of your acceleration. So instead of placing flags on the ground, let's create a different course here. Little markers. We could make a string here and tie little markers onto it. And the first 2 markers are only 10 centimeters apart, and then 20, 30, 40, 50 centimeters apart. But what we're going to do is we're going to race through this course, and instead of being at one of these markers every second, we're going to be at it every 1/10 of a second. So we're going to race through that course very, very, very quickly, maybe faster than anybody could run. But if we go 10 centimeters in 1/10 of a second, we just averaged 100 centimeters per second. And then if we go 20 centimeters in 1/10 of a second, we average 200 centimeters per second. And then 300 and 400 and 500. So our acceleration is a change in velocity over time. We changed our velocity by 100 centimeters per second every 1/10 of a second. So our acceleration would have been 1,000 centimeters per second squared. Now, centimeters per second squared, there's a new unit for that, and it's called gals. 1,000 centimeters per second squared is the same thing as 1,000 gals, and that is a unit of acceleration named after, I hope you guess, Galileo. And maybe in high school you don't see that too much, but it is a unit that we sometimes use. 100 centimeters is a meter, so 1,000 centimeters would be 10 meters. So if we raced through this course and we were at one of those flags every 1/10 of a second, we would have been accelerating at 10 meters per second squared. All right, let's flip this around. If we raced through this course backwards, we would have had a negative acceleration. We would have been losing 10 meters per second every second. And then let's flip this course back around so we're going through it the right way again. But let's talk about relative motion. We could have the course being stationary and the runner racing through a stationary course, or we could have the runner be stationary and the whole course racing past the runner. Relative motion doesn't matter which thing is moving, the results would be the same. So why am I talking about that? What we're going to do is we're going to create a little course here by having a string and little washers tied to the string. These washers are 10 centimeters apart. These two are 20, 30, 40, and 50. And then we're going to just hold that string up and then let gravity do the accelerating of this whole course. If gravity accelerates that uniformly, it should hit the ground in equal periods of time. So the time it takes these two to hit and the time it takes those two to hit and those two and that one, if they hit in equal periods of time, It was accelerating uniformly. So let's take a look at that here. And it looks like it was very fast, so a little harder to see. So let me slow that video down and see if we can tell if they hit in equal periods of time. Still maybe a little hard to see, so let's import that sound into Audacity and graph it and watch. Here it goes. So if they hit in equal periods of time, we could see these little spikes as when it was hitting, and it really does look like they hit in equal periods of time. So it looks like objects in free fall do accelerate uniformly. And again, I'm saying that they're in free fall because they're not traveling fast enough to have an appreciable amount of air resistance to appreciably change the acceleration. So they do accelerate uniformly. Then the question is, do all objects in free fall accelerate uniformly at the same rate? Now you might know the answer to this already, but we have to understand why. And we're actually not going to get into that now. When we get into Newton's laws, we'll be able to explain why all objects fall at the same rate. And it was Galileo who performed a famous experiment by dropping a heavy object and a light object off the Leaning Tower of Pisa, and they did hit the ground at the same time, so heavy objects and light objects fall at the same acceleration. Well, these don't, and obviously it's because of air resistance. But let's see, if I were to drop a book and a piece of paper, we know the book's going to hit the ground first, but which one had more air resistance on it? You might be tempted to say that it was the paper, but it is actually the book that had more air resistance. Because remember, the faster it goes, the more air resistance there is. This book and this paper have about the same cross-sectional area, and the book was traveling faster, so there must have been more air resistance on it. So this will make more sense when we talk about Newton's laws as well. Can't wait till we get there, huh? If I put a piece of paper under the book, then you can see, yeah, the paper is going to fall at the same rate as the book because the book might be forcing the paper to fall faster than it naturally would fall. But if I put the book under the paper and then drop them, the paper doesn't just float away and the book falls fast. They now fall freely. And that's because the book is clearing the air out of the way, allowing the paper to freely fall. And hopefully you've seen a demonstration, a video of this somewhere, but if you were to put a feather and a penny in a vacuum and get rid of the air, a penny and a feather would fall at the exact same rate. And that experiment was done on the moon. So here's a quick video from Commander Dave Scott of Apollo 15.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
So they did fall at the same rate, and that's because there is no air on the moon. The gravity of the moon is a lot weaker, and it wasn't strong enough to hold the air against the surface. Whatever air there may have been on the moon at one time, the air had long since escaped. So all objects do fall at the same rate, and the question now is, at what rate do they go? And this is where I'm explaining to you that we will talk about why they fall at the same rate, but we have to get into Newton's laws of motion first. So now the question is, at what rate do all objects accelerate? And it is different in different places on the Earth, but you can go to the NOAA website, the National Oceanic and Atmospheric Association, and or do a search for gravity predictor, and you can type in your zip code and get your latitude and longitude, and it will tell you what gravity is for your location on Earth. So where I live in Arvada, Colorado, gravity is negative 9.79604 meters per second squared. And it's different in different places. And here that unit of gals is here again. So we say that the acceleration of gravity, acceleration subgravity, anytime we use a subscript, we're trying to indicate which acceleration we're talking about. Because a car traveling down the road could accelerate at a very different rate than if you drop a car off the bridge. But about 9.8, 9.80, typically the acceleration you see throughout Earth. It varies slightly. It is negative because it is an acceleration which is in the down direction. So we say it's negative 9.8. Instead of saying the acceleration of gravity, we could just say g. So if we drop an object anywhere in the world, it's going to accelerate at that rate there. But if we drop an object in the United States, it would accelerate at this rate here. Well, those are the same rates, just meters versus feet. If you drop an object in America, it's going to change its velocity by 32.2 feet per second every second. And on an AP exam or any other test, often you can just say, hey, that number there is really, really close to negative 10 meters per second squared. Just getting an idea for acceleration, you can just kind of round up and say, hey, that's kind of close. So negative 10 meters per second squared is around a number that is close enough that when we're doing multiple choice questions on tests, we can absolutely use that number. So what that means is if we drop an object, and if it were in free fall, every second that goes by, it will change its velocity by 10 meters per second, every second. So when you drop it, every second that goes by, it's going to change its velocity by 10 meters per second. So graphing velocity and time, we get a straight line, and the slope of that line gives us the acceleration. We can see that the slope remains constant, so it tells us that the acceleration is uniform. An object in free fall accelerates at approximately 10 meters per second squared. Now, Felix Baumgartner jumped off of a hot air balloon platform really high up in the atmosphere, 128,000 feet, about 38,000 meters. And there's so little air up there that he was pretty darn close to true free fall. And every second, he went faster and faster and faster by about 10 meters per second every second. And he reached a velocity of over 800 miles per hour. He broke the sound barrier just by falling in gravity. So when he jumps, every second that went by, changing his velocity by 10 meters per second every second. All right, we have this cannon that we're going to shoot a cannonball straight up at 20 meters per second. And we could just plug numbers into this equation and get an answer, but I'd like to just maybe see if we can think about it more instead of having the equation just do magical work for us. But if we shoot it up at 20 meters per second, knowing what we know about gravity, can you already figure out how long that ball will be in the air? Well, if we shoot it up at 20 meters per second, we know in 1 second gravity will slow it down by 10 meters per second. And the next second it will come to a stop. It will turn around and go faster and faster. So here we have the fuse. The fuse is going to burn down. It's going to go boom. Every second, gravity changes its velocity by 10 meters per second. And it looks like it's going to be in the air for 4 seconds. The total time in the air is called the hang time. That's just from when it left the ground to when it came back to the ground. Now let's look at this equation and see if we can make sense of that equation. This is an instantaneous velocity. It's how fast it's traveling in the x direction at this instant in time. And maybe we should have adapted our equation and put y's here because it's going to be in the y direction, but that's okay. So this is our initial velocity in the x direction and how fast we're accelerating in the x direction. And again, we could plug y's in there and talk about the y direction. The main thing that helps us understand this equation is that when you shoot an object up, it has positive velocity at 20 meters per second. When it comes back to the ground, as long as there's no air resistance, it will hit the ground with the same speed, but just opposite direction. And this is the acceleration of gravity. So we subtract 20 from both sides, we get minus 40. We have to divide both sides by negative 10, and we find that the time would be 4 seconds, just what we found it there. All right, now we're going to shoot the cannonball even faster up. We're going to shoot it up at 50 meters per second. And hopefully you can see that it's going to be in the air for 10 seconds, because every second its velocity is going to change. After 5 seconds it comes to a stop, and then it's going to take another 5 seconds to get back to the ground. Hang time was 10 seconds. Same thing, it is shot up and it comes to the ground at the same speed but just opposite direction, and this is the acceleration. So we solve this equation, subtract 50 from both sides, divide both sides by negative 10. It's going to be in the air for 10 seconds. Now there's a lot going on in this graph. We have our cannonball going to be shot up. We have a graph of velocity and time, and then we're just graphing the velocity on a number line. I know it's going to be a lot to keep track of, but here it goes. It's just going to be a straight line because the gravity is uniform. But what I want us to see is particularly what happens here at 5 seconds. The ball was stopped. Okay, so right there at 5 seconds, it had 0 velocity. It was stopped. But was it accelerating at that moment? And it's a little hard to see, but remember the slope of this line tells us the acceleration. Rise over run, it dropped 10 in 1 second, so its acceleration was negative 10 meters per second. But right here it had 0 velocity, but the slope of that line is still negative 10 meters per second. It's like on this thing here, there was a moment when its velocity was 0, but it was passing through 0. It was passing from going up to now going down. Right at that moment, it was changing its direction. So it was changing its velocity. So here's an example where it can be accelerating while stopped. And that's odd. And then we looked at the other example with that motorcycle going 220 miles per hour. It had a bunch of velocity, but the acceleration was 0. It just means the velocity was not changing. Let's look at this example. Now the cannon is on the top of the roof. We're going to shoot it up at 20 meters per second, and then we're going to see how fast it's going to be going 5 seconds after it was shot. So same thing, we go boom every second, so 2 seconds, 3 seconds, 4 seconds, and 5 seconds. After 5 seconds, it's going to be going 30 meters per second. This was its initial velocity. This is the change in velocity due to its accelerating for 5 seconds. And that's how fast it would be going in the down direction. Now this is a fun one. We're going to just shoot this down at 20 meters per second. So the moment it leaves the barrel, it's going 20 meters per second. But the moment it leaves the barrel, it's in free fall. Gravity takes over, and every second it's going to be going 10 meters per second faster. So we shoot it at 20, and after 1 second, 2 seconds, 3 seconds, 4 seconds, after 5 seconds, it would be going 70 meters per second. This was the initial velocity, and this was the change in velocity due to it accelerating for a period of time. Its instantaneous velocity is going to be 70 meters per second down. Now, I like poking fun at Hollywood movies because often they just insult our intelligence. But here is a video clip from Transporter 2.
The files. You really want to play superhero, don't you? Well, let's see if you can fly.
So can you guess what was wrong with that video? Well, these little vials, whatever they were thrown out of the window a moment before he jumped out of the window. So which means these have been accelerating for a little bit longer period of time than he is. And because they've been accelerating for a longer period of time, they're going faster than he is. And there's no way he could have caught up to them. Sorry. So here's a vial, here's a person chasing after him. I'm going to show a speedometer on the vial, and in my animation this person's going to jump 1 second later. I'll show a speedometer on them. So there the vial begins to fall, there they begin to fall. The vial was traveling this fast. They jumped a moment later or a second later, so they're only traveling this fast. Anytime you have two objects and the thing in front is going faster than the thing behind, the space in between them is going to be getting greater and greater. There's no chance of catching it. And here's a really neat video of a bar here that has a bunch of little water spigots, and it can very precisely control when it drops the water. So as that water falls, they can turn it off and on and create neat shapes. But look what happens to the shape of those shapes. They stretch out as they fall, and that's because the bottom of that shape is falling faster than the top of that shape. So that's a little bit about free fall and the acceleration of gravity. Lots more to come with that. So I hope you're enjoying.